These are notes for 9.5 on the derivative of an inverse function. I've written down the first two things that you need to remember. So you have learned these before in the past. So to remind you, two functions, f and g, are inverses of each other if and only if f of g of x equals x and g of f of x equals x. Our second statement says that a function's inverse is a function if and only if the original function is one-to-one. And that means that it passes the horizontal line test. So this is just background information to remember. We might recall some of this as we go through the lesson here. We're going to start with kind of a review. Okay, so let's talk about the one-to-one here. So we'll take a graph like the line y equals x, which is a function itself. So, let's call this f of x. And so its inverse is also a function. So this is a function because it passes the horizontal line test or vertical line test. For any vertical line we draw, we only pass through the function once. So it's a function itself. And then our horizontal line test, if I do a horizontal line here, we only pass through the function one time as well. So that means f inverse will be a function. So for another example, let's talk about y equals x squared. All right, so we'll call this g of x. So g of x passes the vertical line test. So for every vertical line we draw, we only pass through the function one time, and it is a function. However, if I draw any horizontal line, there are a lot of times where we pass through the function twice. So this means that the inverse of g will not be a function. In other words, g of x is not one-to-one. But back over here, f of x is one-to-one. Okay, so the next thing we're going to do is practice finding an inverse. So let's say f of x is x minus 1 squared minus 3, but only for values of x greater than or equal to 1. So you'll notice this was a parabola, but now it's only half of a parabola. So we're going to start with a sketch. So this parabola would be moved 1 unit to the right and 3 units down would be its vertex. It would open up on both sides, but because of this domain that says x must be greater than or equal to 1, it's only the right half of my parabola. So this is f. So we are going to want to sketch its inverse, and we can do this from the graph. So we can do it now. Whenever we draw an inverse, remember it's just a reflection over the line y equals x. So if we reflect over that, then we're reflecting all of the points such as taking the point here, 1, -3 from my vertex of F, and inverting those values. So 1, -3 becomes -3, 1. And I could do that with the next point, which was 2, -2. So that becomes -2, 2. And then I've got this point where they both cross the line y equals x at the same time. So that's another point. So here we go. And I have the inverse of F drawn. So it's just a mirror image over the line y equals x. So you should be able to see that there. Let's go on and do part B. So in part B, we are going to solve for the inverse of F. So just like we did with the coordinate pairs, we're going to switch x and y in our equation. So we're going to start with the original, which is y equals x minus 1 squared minus 3. We're going to switch places with x and y. And now it becomes x is equal to y minus 1 squared minus 3. From here, we want to get y by itself, so we start by adding 3. And then we're going to get rid of the exponent by square rooting both sides. You want to be careful. Whenever you square root something, you always get that plus or minus. Although we're going to have to determine which part we actually want to keep. Do we want both? Do we only want the positive? Or do we only want the negative? This is actually going to be based on the domain of x that we were given here. So let's finish up first by adding 1 over 1 plus or minus root x plus 3. All right, so if x is greater than or equal to 1, then x is a positive value. So I want to keep those positive values for y over here, and we'll go through that a little bit more in a moment. So y is actually my inverse now, f inverse of x. 1 plus the root of x plus 3. So that'll be my inverse function. So let's talk about how I know that I want those positive values. So remember when we just switched places with x and y. So 1, -3 became -3, 1. 2, -2 became -2, 2. And this just kept going. So when we list the domain of f, we get values like 1 and 2, and everything greater than 1. X is greater than 1. Or we would write 1 to infinity. When we look at the range of f, we have lowest -3, -2, and so on. It keeps going. So y is greater than or equal to -3, or we would write that as -3 to infinity. Now, there's something you should remember about this, comparing it to the inverse, and that is that the range of f inverse is the domain of f, and that the domain of f inverse is the range of f, because we just switched places with all the values. So when I was looking at the domain here, x has to be greater than or equal to 1. Okay, that means that my range, my y values for my f inverse of x, they had to be positive values as well. So just a little shortcut here that those are positive values, and that told me to just keep the positives when I got down here to my inverse function. Next, we're going to do part C. And before we do, we're going to go ahead and call the inverse of f g. I'll just make this a little bit easier to refer to them as functions f and g, and that they are inverses of one another. So knowing that, we want to evaluate a few things. We're going to start with f of 3. So let's plug 3 into function f. We get 3 minus 1 squared minus 3, which is 4 minus 3. So we get a value of 1. So this gives me a coordinate pair 3, 1. The second thing we want to evaluate is g of 1. So plugging 1 into the inverse will be 1 plus the square root of 1 plus 3. So that's 1 plus root 4, and 1 plus 2 is 3. So we have the coordinate pair 1, 3. So this shouldn't be a surprise since f and g are inverses of one another. Their x and y's switch places. Now, I think something that will be a little surprising to us is the next part. So the third thing we're going to evaluate is the derivative of f at 3. So let's go back and take the derivative of function f. So we'll just make some space over here on the side. So f prime of x. So we bring down 2 times x minus 1 to the first power. Chain rule gives us a derivative of 1, and the derivative of negative 3 is 0. So this is the derivative of f. If we evaluate this when x is 3, we have 2 times 3 minus 1, or 2 times 2, which is 4. Okay, the last thing is the derivative of g at 1. So we're going to go back and find the derivative of g. So we have the derivative of 1 is 0, and the derivative of our square root is 1 over 2 times the original root, which is x plus 3, and the derivative of what's inside, which would just be 1. So if we plug 1 into our derivative here, we have 1 over 2 root 1 plus 3. So this is 1 over 2 root 4, and 2 times 2 is 4. So what we want to notice is the points swap places with x and y, and at those corresponding points, my slopes are reciprocals. This happens every time. Okay. If we go back up to our function and we were to draw these lines or plot these points, we should be able to see. So let's go to function f at the point 3, 1. So right about here, we should have a tangent line, and the slope of this tangent line should be 4. On the inverse, at the point 1, 3, which would be here, we would have a tangent line, and its slope is 1/4. So at these corresponding points, we have reciprocal slopes. And that's going to bring us to this equation, this formula that we have. So the slopes, or derivatives, Okay, so the derivatives of the inverse functions at the corresponding points are reciprocals. So this formula says g prime at A is equal to 1 over f prime at g of A. So remember, since g and f are inverses, so we'll include that. So g of A is equal to some value, and that value corresponds to what's in function f. So that's what we had here. So g of A, g of 1 was 3, and then f prime at 3 was 4, and then this became 1 divided by 4. That was the slope of the inverse function. So it's just a formula that we need to be able to use, and I'm going to walk you through an example of how to use it. So in this example, f of x is x cubed minus 4 over x, and x must be positive. We don't want x to be 0 since it is in the denominator, but this also helps so that f is 1 to 1. So that means its inverse is also a function. So we'd like to find g prime of 6 given f and g are inverses. So since they're inverses, our little formula applies, and that formula was g prime of, let's see, we'd like to know 6. G prime of 6 is equal to 1 over f prime of g of 6. So this is a formula that we do need to remember. We are going to start with finding g of 6. So that is step 1. So g of 6 is some value. So this is an x, and we're looking for y. So what you'll remember, because they're inverses, is that function f of something equals something. So their x's and y's should switch places. So f of some value x should give me a y value of 6. And I know what function f is, so I'm going to set my function equal to 6. So I have x cubed minus 4 over x is equal to 6. So we can try to solve this by hand, multiplying everything by x. But it seems like we run into some trouble here, something that I can't factor, or at least not very easily by hand. So you might grab your graphing calculator and just graph this function. And you'll just look for the 0. Remember, that's what it means to equal 0 here. So it comes out to 2, which is pretty nice. So this tells us that f of 2 equals 6, which means g of 6 is equal to 2. So that is this inner value here. So now my function becomes 1 over f prime of 2. Okay, so this is the derivative of f at 2. So now my second step is this. So step 2, find the derivative of f. So we have 3x squared and plus 4 over x squared. So now we just plug in 2. So 3 times 4 plus 4 divided by 4. So 12 plus 1, which is 13. And then this just goes right back in here and gives me an answer of 1 over 13. So that is how we do these problems. The last thing that I have to show you is really just a definition. Of this word monotonic. So you'll see things that say a function is monotonic decreasing, or maybe monotonic increasing. And this just means that it is always decreasing or always increasing. And this will come in most often with your first derivative test, since that is what tells us when functions are increasing or decreasing, or when they change from increasing to decreasing. So I am going to do an example with you here. So we have this natural log of x minus 3. Now, if you remember the graph of a natural log of x, you probably know that this function is always increasing. The minus 3 simply moves the graph to the right 3 spaces. But we can show this by doing our first derivative test. So the derivative of any natural log function, always 1 over the stuff inside times the derivative of what's inside. So it'll just give us a 1. And then we get no critical numbers from this except x can't be 3. But I think we already knew that because my natural log function won't allow for 0 or any negative number inside anyway. So my function itself does not exist for any values less than 3. And only for numbers greater anyway. So there's nothing that's going to make this fraction equal 0, so we're not going to get any critical numbers at all. So all that means is that we have no values to test over, and that the function is always doing the same thing. So it might be always increasing, always decreasing, or maybe it's just a constant function, a horizontal line. We just know that's not what's happening. So we plug in any test number we like. So anything bigger than 3 here. So let's say we plug in 5. So we would get f prime 5, 1 over 5 minus 3 is 1/2, which is positive. I could plug in 20. 1 over 20 minus 3 is 1 over 17. Again, positive. So we interpret this whenever our first derivative is positive, we know that f is increasing. So we have here that f is monotonic increasing. Just keep in mind that you may come across a function whose graph you don't know what it looks like, and so the first derivative test will tell you that.